So for a rectangular equation, it would be x comma y. For a polar equation, it is r comma theta. And I'm going to draw a picture to show you what I mean by that. And I really feel strongly that it should be theta comma r, because you have to rotate first and then move. But anyway, no one asked me my opinion, and it's r comma theta. So here is your coordinate plane. And so like, say, here's where your point is. And I'll color code this. You won't really be able to see the colors on here, but when I take a picture and post it, you'll be able to see. R is the distance from the center. So that's R. And theta is how much you rotated. And that's why the unit circle, like this is based on the unit circle entirely, like all of your rotations. So it's how far you went from the center and then how far you rotated. And really you have to rotate first. So it should really be the other way around. But anyway. And so we don't call this the origin anymore. It's called the pole. Like the North Pole, it's called the pole. And it is 0 comma theta, where theta is any angle. And I want us to just think about that for a second so that can kind of sink in. If R is 0, like if you didn't go anywhere, it doesn't matter how much you rotated. You could rotate a zillion pi and it doesn't matter because it's still 0. So it's 0 comma any angle. Make sense? Okay. So let's practice plotting some points. And what you're about to find is that there's multiple ways you can do this. So for this one, you would rotate to pi over 3, and I just have all your pieces of the unit circle on here. So like this is pi over 6, this is pi over 4, this one's pi over 3. Okay, so you would rotate to pi over 3. So that's this little section of the spider web. And then you would go 2 units out from the pole. So that point would be right here. We're just plotting points. We're just learning how to, like, where the point is going to end up. So for this one, you would rotate backwards pi over 6. So what quadrant does that put you in? The fourth, it would be this little piece of the spider web here. And you're going to go 3 units out from the pole. So that would be right there. So then look at number 3. If you rotate 11 pi over 6, that's practically the whole way around. And then if you go 3 units away from the pole, it's going to be right here. So do you see how these are in the exact same spot, but they had 2 different amounts of rotation? There are an infinite number of ways you can write a point, because every time you just add on another rotation, you land in the same spot, which is cool and also a little bit overwhelming. So don't think about it too hard, but there's, you know, an infinite number of ways you can write this. All right, and then this one, you're going to rotate pi over 4. Watch me point to it because I kind of don't have a better explanation than here. Look, you would rotate to pi over 4. That's this piece of the spider web. Do you see me pointing at that? See how that's a -4 though? So instead of going 4 in that direction, you go 4 in the opposite direction and it ends up over here. So when you have a negative, you go like out the other side and just go in the opposite direction. So from our unit circle, we get these triangles. When you rotate whatever your angle is, like we're going to put theta there. Oh, whoops. You get these triangles created like out of the unit circle. Now for the unit circle, the hypotenuse would always be 1 because it's 1 unit. I'm going to call it R here because, again, we can go further than 1. So I guess I shouldn't have said from the unit circle, but that's where the idea comes from. Anyway, I'm going to put R there for how far you go from the pole. This is X and this is Y. Ringing any bells? Yeah, you did.
No, we did. You're right.
And then when you do the unit circle, R is always 1. Here, R could be any number, though, so just leave it as R. So we've got our good old Pythagorean theorem, which would be x squared plus y squared equals r squared. So that's back from geometry. And then in pre-calc, you did your trig, so sine, cosine, tangent. So sine of theta would be what over what, using this triangle here? Good. Opposite over hypotenuse, so y over r. And when r is 1 with the unit circle, that's why sine is the y value. Remember that? Okay. And then cosine would be x over r. And again, when r is 1 for the unit circle, that's why cosine is your x value. And then tangent of theta, y over x. And that's why tangent is sine over cosine. It's y over x. Opposite over adjacent, that's where all that comes from. Okay, so the idea here is we want to be able to convert between rectangular and polar. Okay, so to convert rectangular form to polar form, that means you have x and y, you need r and theta. So if you have x and y, you would use the Pythagorean theorem to get r. Like you would plug in your x and your y and you would get r. Following me there? Okay, so you're going to use your Pythagorean theorem to get r. And if you have x and y and you're missing theta, theta is the thing you're trying to get, which one of these would you use? If you have x and y, do you see how tangent involves the x and the y? Okay, so you would use that one. Tangent of theta would equal y over x. I'm going to do one more step to that because you see it this way often. To get the theta by itself, like if you're trying to find theta, you would have to anti-tangent. How would we write that? One, yeah, and it's, I'll take that, but it's tangent, what word? Inverse, good. Or arctangent, good. But you see tangent inverse a lot with these because of that reason. So tangent inverse comes up a lot, and it looks scary to people because it's tangent inverse. Now, if you want to go back the other way, if you have polar and you want to get rectangular, that means you have r and theta, you want x and y. So Pythagorean theorem is not going to do you any good. You have r, but you're missing both of these. So that's not going to work. How could we get x? Like if we have r and theta, but we need x, that's the first thing we're trying to find. Cosine. Good. You would use the cosine one. How would you get x by itself here?
Y.
R over, good. So x equals r cosine theta. That's how you would get x. So if you have r and theta, but you're missing x, that's how you would get that. How would you get y? Good. And again, you would multiply the r over, so it would be r sine theta. With what we're going to do next time, if you don't remember anything else from today, remember this, those two. That's huge in this unit, and you got to have that down, okay? X equals r cosine theta, y equals r sine theta. So let's practice converting a few. Convert to rectangular form. So this is polar r theta, and I usually just label that because that helps you remember what you've got. So we have r and theta, we need x and y. This is the formula that we're going to use here, the two formulas we're going to use. So let's find x first. X equals r, which is 2, times cosine theta, which is pi. And then you just have to work that out. So what's cosine of pi? -1 times 2 is -2. And then y is going to be r sine theta. So that would be 2 sine pi, which would be 0. I always suggest drawing a little picture so that you can see it visually. The point -2, 0 would be right here. And I just want you to make the connection. Does that make sense that in polar, it would be 2, pi? Like you've rotated pi and then gone 2 units in that direction. Okay, I like to see the visual. Like I need the visual. It helps me. Okay, let's try it again. So this is r, this is theta. This one's going to be a little bit messier because I stuck a square root in there. So x would equal what? How would we set that up? Good. Square root of 3 cosine pi over 6. And then all you have to do is remember everything from pre-calculus. So what's cosine pi over 6? Good. So square root of 3 times square root of 3 would just be 3. So it'll end up just being 3 over 2. All right. And then y is going to be square root of 3 sine pi over 6. Easy enough, and then all you have to do is remember everything from pre-calculus. So that would be 1/2. So square root of 3 times 1/2, which would just be square root of 3 over 2. And we're going to draw, humor me, we're going to draw it so that you can visualize what's going on here. If you rotate pi over 6 amount, that would be like right about there. It's not to scale, okay? But if you rotate pi over 6 amount and then go square root of 3 in that direction, I don't have memorized what square root of 3 is, but I know it's like 1 point something. So like if I go about like 1.5 away, again, this is not to scale, it would be like right about there-ish, okay? But does that make sense that it would be 1.5 comma, like whatever that is? Like, at least make sure it's in the right quadrant is all I'm saying, okay? Now we're gonna do it the other way around. We have X and Y, we're gonna convert it to polar. So we need R and we need theta. Those are the two things that we're trying to find. So what would we do to get R? Let's find R first. Good, it'll be -1 squared plus 1 squared equals R squared. So I'll just be, this is going to turn positive. So 1 plus 1 is 2 equals R squared. And so you would square root that. Cool. How do we get theta? Yeah, now it's inverse tangent. And I wrote it that way so you guys can get used to seeing that because that does come up. I would still write it this way, tangent of theta equals y over x, because it just looks a little nicer, okay? So tangent theta equals y over x. Now 1 over 1 is just 1. It's just, it'll be -1. And then all you have to do is remember everything about the unit circle. And this is where visualizing really is necessary when you go back the other way, because we have to know what quadrant this is to figure out how much we rotated, because with polar, I mean, like, there's an infinite number of options. So you kind of have to be able to visualize it here. What quadrant is -1 comma 1 in? In the second quadrant, it would be right there. So what we're trying to do is figure out how much we rotated to get into the second quadrant, and tangent ends up being -1. I'm going to close my mouth and let you guys think about it. But what you're trying to figure out is that amount of rotation. Good. Why is it 3 pi over 4? Both sides would be square root of 2 over 2, except one of them would be negative, and anything over itself gives you 1, okay? So it would be square root of 2 comma 3 pi over 4 is our like actual point there. What's another way you could write that though? Square root of 2 comma, what if you went backwards the other way? Like what if you made your angle negative? It would be square root of 2 comma -5 pi over 4. What if you added on 2 pi for an extra rotation? Do you get what I'm saying? There's like an infinite number of right answers. You just have to be really careful. All right, so this is X and Y. We need R and theta. So to get R, you're just going to do Pythagorean theorem. So that would be 4 equals R squared. R is 2. And then we're going to use tangent to get our theta. So tangent of theta equals y over x. That's going to be 2 over 0. And that's undefined. That means there's an asymptote there. Do you guys remember what tangent looks like? How there's all those asymptotes and the things that look like cubic functions in there? Okay, so when that happens, what I would do is go back to the visual. Just always rely back on the visual. The point 0, 2 would be right here. So that's why it's 2. We went 2 units away from the pole. How far did we rotate to get there? Pi over 2. And there's an asymptote at pi over 2 in your tangent function. That's why that's like that. So it would be 2 comma pi over 2. What's another way you could write that? 2 comma, what if you went backwards? -3 pi over 2. Or you could do -pi over 2 down to here, and then do a -2, like to the opposite direction. Do you see what I'm saying? Anyway, you have those. We'll do these 3 and then we'll do a break. So we're going to graph each polar equation and then convert it to rectangular form. The difference now is they're not just points. We're not just like plotting one point. Where did we have that? It was on the front. So see here, we were just practicing like where do these end up? Now we're doing a whole graph, okay? So if it says r equals 2, that means you want to be 2 units away from the pole at all times. What is that going to look like? Be a circle at 2. It'll look like this. I was trying to like highlight it and make it actually show up. Now, when you go to convert it into rectangular, that means you need something with an X and a Y in it. If all you have is R, it'll be your Pythagorean theorem. It'll be X squared plus Y squared. In this case, 2 squared, which is 4. And that's your rectangular form. Does that ring any bells from geometry? I know geometry, how many years ago was that? Like 4 years ago for you guys, 5 years ago? It's a long time. But do you remember the circle equations, even sort of like x squared plus y squared equals r squared? Like you actually learn x squared plus y squared equals r squared in geometry. Like if you had x squared plus y squared equals 16, it'd be a circle with a radius of 4. It was 16, square root of 16 is 4. Anyway, it did happen. It was, how many years ago was geometry? You had geometry, then you had algebra 2, pre-calc, calc AB. Now this is 4 years ago, long time. All right, for this one, all we have is theta being pi over 3. You want your amount of rotation to be pi over 3 all the time. So you would rotate to pi over 3. Do you see how that's this part? And it would just be that line. So we got something linear, which is kind of cool. Now, if all you have is theta, and you need it in terms of x and y, we're going to need to use tangent. So it'll be tangent of pi over 3 equals y over x. And then we just need to do tangent of pi over 3. I'm going to draw a triangle for you so that you can see this. I recommend you do too. Here's pi over 3. What are going to be the sides of the triangle? For pi over 3, what would our sides be? 1/2 goes here. And then square root of 3 over 2 goes here. Yeah, okay. You made me second guess myself there. I knew it was right. So how do you do tangent? Tangent, how do we get tangent from this? 1/2. Okay, now don't write this because it looks absolutely awful. But what's going to happen? Yeah, and you get square root of 3 over 1, which just is square root of 3. And then what we're going to do is just multiply the x over. So you get y equals square root of 3x. It is like y equals 5x or y equals 9x. You have a slope of square root of 3. Do you see what I'm saying? It's y equals mx plus b. It's just b is 0. And your slope is square root of 3, which is kind of cool. I made this one a little bit more complicated. You now have r in terms of theta, which is how these are mostly going to look. Now this one says secant. So do you want to try and use the sine formula or the cosine formula if it says secant? Just like instinctually, which one do you? Cosine one. Good. Okay, cool. Our instincts are there. So we're going to use this. Cosine theta. Or I'm sorry, x equals r cosine theta. You don't have to write it again. I'm just going to write it down so that you have it. X equals r cosine theta. So what was r for this? R is secant theta. So you get secant theta times cosine theta. And you guys were right when you said to pick that one. And here's why. What happens with those? Since they're reciprocals, it cancels and you get 1. What would the graph of x equals 1 look like? Forget all of this, just x equals 1. Yeah, it's just a vertical line at 1. So here's 1. You just get a vertical line at 1. If this had said r equals cosecant, then we would have done sine and we would have ended up with a horizontal line. Cool, all right. I always worry that this is going to be like pulling teeth, but you've been with me every step of the way, so that's awesome. We'll do another little break and then we'll do the last 2 graphs then.
pi, one longer pi, another way.
All right, so now we are going to sketch more intricate graphs, and then I'll show you how to check it on the calculator, because if you get allowed a calculator, it's actually kind of nice. So what we're gonna do is make a little table for theta and r. When I say a little table, we're gonna actually plug in quite a few things. I want us to go around our unit circle from 0 to pi for this one. So let's go and pull all the values from our unit circle from 0 to pi. So we get 0 pi, pi over 6, pi over 4, pi over 3. I'm going to stop talking because that's really annoying, but if you could just like write them all down from 0 to pi, that would be good. This kind of reminds me of when we did Euler's method and we made all those tables. Except, for heaven's sake, one that long for Euler's method would be awful. Usually you only have to do like a few steps. And so, like with a rectangular equation, you know, you make an XY table, you plug in X, you get Y. We're going to plug all those thetas in and get R and then connect them, okay? So let's plug in 0, and this is where you have to know your unit circle. If you plug in 0 pi, 0 times 3 is 0, cosine of 0. Good, times 2, 2. Pi over 6, times 3, be pi over 2. Cosine of pi over 2, 0. You know, I'll do one more with you, and then I think I'm going to just shut my mouth and let you guys try and like work on that together. Try and fill out the rest of it. Pi over 4. If you plug that in and multiply it by 3, you get 3 pi over 4. That's in the second quadrant. Cosine of 3 pi over 4 would be negative square root of 2 over 2. And the 2's would cancel. So it would just be negative square root of 2. All right, so we got all that filled in. Now we're going to plot them and connect them. Maybe let's do this. Watch me, and then I'll pause, and then you can copy it down. Because if you do want, like, if you're trying to look and look back, it's going to mess you up. Okay, so let's just do this together. You rotate nowhere, so you're still at 0 pi, and you go 2 units in that direction. So that would be right here. So that's where we're starting. And do you remember how parametric had like a orientation to it, like a direction that you go? This does as well. So you have to be careful with, like, we don't put little arrows on them, but you have to be careful with the direction. All right, pi over 6 would be right here, but we didn't go anywhere, so we're at the pole. So remember, this was our first point. This is our second one. Pi over 4 would be right here. Oh, but it's negative square root. Square root of 2, I don't know exactly what that is, but I know it's in between 1 and 2. Can we just go with 1.5 for like this is going to be perfect, right? Okay, so watch me point to it. Here's pi over 4. But we're going to go backwards 1.5. It's going to put us like right about here. So again, try to remember what order we did these in. Pi over 3 is right here, but it's a negative 2, so you're going to go out the other side. So that's going to be right there. Want me to start connecting it so you can see what it looks like? So we start here. We're going to connect to that one. And then come down here and connect to that one. Like that's what we've gotten so far. All right. Pi over 2, nothing. Well, if you didn't go anywhere, then you're at the pole. So now we're back to the pole. 2 pi over 3 would be this piece of the little spider web. And we go 2 in that direction. So that'll put us right there. All right, 3 pi over 4 right here in the center, square root of 2, I don't know, like 1.5, good enough. Back to 0. And then for this one, if you go to pi, that's over here. Like if you rotate to pi, but we went negative 2, so it's the opposite direction, and it puts you right back where you started. Watch me trace it. We started here. We went like this, back to the center, then up here, back to the center, and then back to where we started. And if you kept putting more values on the table, it would keep going around and around and around and around. So on your calculator, oh, sorry. It's a little 3-leaf clover. I wish they were called clovers, but these are actually called the roses. That's what these graphs, these types of graphs are called. They're called the roses. But I think they should be the clovers. They look like clovers. This does involve a little bit of art to it. I'm not grading your art skills, but yeah, it is like a little roundabout. So what we're going to do on here is we're going to go to mode right next to second. Keep it in radians. But down here, do you see where it says function? And then remember we did PAR, we did parametric. What do you think this next one over is? Polar. Go and put it in polar mode. That's sequences. We aren't going to do that though. I've never done anything with that. Oh no, we're going to do the sequences. We're just not going to do them in the calculator.
What is a view?
Well, I've never used it. I just do them by hand. They're like non-calculator questions. Anyway, we're in polar mode. Go to y equals, and you will see that it now says r equals. And we're going to type this in. 2 cosine 3 theta. And when you type your x button, it will give you a theta. Do you remember we did parametric and it gave you t? That's why that button says x t theta n. It's just no one understands that until they get to Calc BC, which is like almost no one. So anyway, don't hit graph yet. We're going to go to window and adjust our window. Now, values that we put in here were 0 to pi. So change that theta 0 to pi. I guess you could let it go to 2 pi. It would just go once more around the clover, but it doesn't matter. Now, your theta step, same thing as when we did the t step. If you make it too big, it's going to look boxy because it's only going to connect them for however often you say to. If you make it too tiny, like if you make it 0.0001, it'll be thinking forever and ever and never actually give you anything. Leave it about at 0.1. I never touch that. Okay. And then this is pretty small. See how it only goes out 2 units away? So if you want to get like a better picture, maybe change that -4 to 4. Leave the scales 1. But if you leave it 10, like you're going to have a huge grid with this tiny little clover on it. And I just want you to be able to see it better. So change it -4 to 4 and then hit graph. And try to notice, it does it fast, but do you see how it starts, where it starts, and then as it goes around, it goes in the correct orientation? I know it's like blinking, you'll miss it kind of thing, but you see that? Cool, it's so cool. These are so neat. Go ahead and flip your paper over. I just took a picture of the textbook and put it on. Do you guys still have your textbooks? I told him to take them home and put them under your bed. Did you do that? And you have it somewhere?
It's somewhere.
You got to turn it in before you can get graduation ticket. Anyway.
Oh, wow. All right.
These are called rose curves, and it's cool. And I'm going to have us mess with the calculator a little bit. I want you to play around with this so you can understand what's going on. It will have n petals when n is odd. So do you see how we did 3 theta and 3 is odd and we got 3 petals? Go and change the 3 to a 5 and hit graph. So do you see how there's 5 petals? If n is odd, you just get what it is. If n is even, you get double the number of petals. So if you go back and change the 5 to a 2, how many petals will you get? You'll get 4, and it'll look like a roundabout, like on the highway. Oh, but what happened? Why'd we only get half of it? Why'd we only get half of it? Go back to your window. We only rotated to pi. Can you change it to 2 pi and then we'll get the whole thing? Change it to 2 pi and hit graph and then you'll get the whole thing.
Oh, yeah.
How could I make there be 16 petals? You would make this 8.
Oh, my gosh.
Isn't that cool? Looks like a snowflake almost. How could you make there be 10 petals? 5 won't do it, right? Because 5 is odd, and that'll give you 5. There's no way to get 10 petals. What's another number that you couldn't get? You couldn't get 14 petals because half of that would be 7, but then 7 is odd. That kicks you into the other category. So look, if you change this to a 7, you'll get 7 petals. This is cool, guys. Cool. These are sweet. All right, we're going to do one more. So make yourself a table, theta and r. And for this one, we can just grab all the quadrant angles. This one will actually be a little bit easier. The reason we can just do the quadrant angles for this one is, do you see how it's just cosine theta? It's not like a 2 theta or a 3 theta or anything. So we can just grab the quadrant angles for them. I love getting to teach this stuff. This is the only class where I get to cover stuff like this. Like we don't cover this in any other class. So I get geeked out when we do this. All right, so let's plug in 0. Cosine of 0. 1 times 5 would be 5. 2 minus 5. -3. Let's plot them as we go along this time, now that I've shown it to you, because I think you'll be able to keep up with that. So 0, if you rotated 0, you're right here. But if you go -3, you go 3 in the opposite direction. So it would be right there. So that's where we're starting. And again, there's an orientation to it. So like that's the starting point. All right, plugging in pi over 2. Cosine of pi over 2. 0. So you get 2 minus 0, which is 2. So that's going to be right here. Now, when you connect those, you will go through the pole. These always go through the pole. And if you set this equation equal to 0 and solve it, you'll get an answer. It's going to travel through the pole on its way there. So this is what we have so far. I forget what this one looks like, so not sure what we're going to get here. All right, pi, cosine of pi. -1 times -5 would be +5. So 2 plus 5, 7. So if you rotate to pi, that's over here. And if you go 7 in that direction, it'll put you right, because you rotate and then you go towards that rotation, like you go in that direction. So now it feels like -7 and it's like this said +7, but pi is over here. All right, so now we're going to connect over to that point. It's like a little snail or something. All right, cosine of 3 pi over 2 would be 0. So this would give you what as like a final answer? It would be 2. So if you rotate to 3 pi over 2, that's down here, and you go 2 in that direction. It's kind of like a heart, sort of, I guess. And then the last one's going to put you back where you started, but you're going to go through the pole on your way there. Like you can't get from here to here without going through the pole. So go back through the pole, and then it'll connect you to where you started. So it looks like the way a second grader would draw a heart or something. I don't know. I didn't draw mine really great. But that's this category. I don't actually know how. I think Lima Con, Lima Son. I don't know. Which do you feel, whatever you want to call it, but like a little lima bean. Okay. So we got this one. But do you see how if you alter the information, like it changes it? Like this one's a dimpled one. It's got a little dimple. Isn't that cute? All right, and then you can end up with other stuff like just plain old circles or something that looks kind of like an infinity symbol. I would encourage you to read this and then play around with the calculator and like make some of those graphs and then alter them and then see what it looks like. Because where we're headed, this is just your foreshadowing, we're going to find the areas inside of these. And if you can't get a graph, you'll be stuck. Okay, so I'd encourage you to, I don't have homework, like a graded homework assignment for you. So I'd encourage you to play around with the calculator, okay?